Imagine that tonight, while you are sleeping, and something appears near our solar system. It is smaller than a city, but it weighs more than the sun. It spins 30 times every second, and from its poles, two invisible beams sweep through space like the lights of a giant cosmic lighthouse. One of those beams is pointing directly at Earth. But the strangest part is that nothing happens immediately. The oceans remain calm, the moon continues moving, people wake up, drink coffee, and complain about traffic. Earth has no idea that a dead star has just appeared nearby. Why? Because even gravity cannot deliver the warning instantly. Our pulsar is 1,000 times farther from the sun than Earth is. Its light, radiation, and gravitational influence need almost 6 days to reach us. For almost 6 days, humanity receives one final period of complete normality. Then the signal arrives. Radio telescopes scream. Satellites detect a wall of energy. The night side of Earth begins to glow with enormous auroras. And 30 times every second, the planet is struck by another pulse. Not with sound, not with fire, but with radio waves, X-rays, gamma rays, and high-speed particles. We have just become the target of one of the strangest objects in the universe. So what exactly is attacking us? A pulsar begins with a star much larger than our sun. For millions of years, that star burns fuel inside its core. Gravity pushes inward, energy pushes outward. The two forces remain balanced, like two people pressing against opposite sides of a door. But eventually, the star runs out of fuel. The outward pressure weakens, and gravity wins. And when gravity wins inside a giant star, it does not win gently. The core collapses in less than a second. Matter falls inward at incredible speed. Protons and electrons are crushed together. They become neutrons. Then the outer layers of the star rebound and explode into space. That explosion is called a supernova. What remains in the center is a neutron star, a dead stellar core squeezed into a ball only about 20 kilometers wide. But calling it tiny is dangerously misleading. Imagine taking more matter than exists inside the sun. Now squeeze it until it fits inside a city. The material becomes so dense that a spoonful would weigh roughly as much as a mountain. There are no normal rooms inside it, no empty spaces between atoms like the ones around us. Matter has been pressed almost as tightly as nature allows. And squeezing the star does something else. It makes the corpse spin much faster. Think about an ice skater. When the skater stretches out their arms, they rotate slowly. When they pull their arms inward, they spin faster. A collapsing star does something similar. Its enormous body becomes a tiny ball, so its rotation speeds up. Some neutron stars rotate once every few seconds. Others rotate hundreds of times every second. But spinning alone does not make a pulsar. A neutron star also carries an extremely strong magnetic field. That field guides charged particles toward its magnetic poles. Energy escapes from those regions in powerful beams. But the magnetic poles do not always point in the same direction as the rotation axis. So as the neutron star spins, the beams sweep across space. Whenever a beam crosses Earth, our telescopes detect a pulse. That is why we call it a pulsar. The pulsar is not actually blinking. We are simply standing in the path of its rotating beam. These pulses can be astonishingly regular. Some pulsars act like enormous clocks floating in the galaxy. Pulse, pulse, pulse. They can continue with such precision that scientists have studied them for navigation and timekeeping. But our new neighbor is not a gentle old pulsar. For this story, we have traced a young, energetic pulsar 1,000 astronomical units away, and its beam crosses Earth 30 times every second. 30 hits every second sounds dramatic, but could a human actually see the sky blinking? Probably not. 30 flashes every second would be too fast for our eyes to separate clearly. And much of the pulsar's energy would be invisible anyway. Radio waves cannot be seen. X-rays cannot be seen. Gamma rays cannot be seen. To human eyes, the beam itself might look like nothing. But invisible does not mean harmless. The first victims would not be people standing outside. They would be the machines above them. Satellites live beyond much of the protection provided by our atmosphere. They contain delicate electronics. They depend on predictable signals. Suddenly, they would be surrounded by intense radiation and charged particles. Some instruments might enter emergency mode. Others could return corrupted information. Communication links could become noisy or disappear, and satellites facing the beam directly might stop working entirely. Within hours, the modern world could begin losing its eyes, ears, and clocks. Satellites help guide airplanes. They track storms. They connect financial systems. They support navigation, communication, farming, and emergency services. Not every system would fail at the same time, but even partial failures would create confusion. Maps could become unreliable. Flights could be delayed. Ships could lose precision navigation. Weather forecasts could become less accurate exactly when we need them most. Then, the invisible attack reaches the atmosphere. Earth is not completely defenseless. Our magnetic field redirects many charged particles. Our atmosphere absorbs much of the dangerous radiation arriving from space. Think of Earth as a small person wearing two shields. One shield is magnetic, the other is made of air. Together, they have protected life for billions of years. But these shields were not built for a pulsar living in our cosmic backyard. The pulsar releases more than beams of light. It can also produce a wind of fast-moving particles. When that wind reaches Earth, it pushes against our magnetic field. The side facing the pulsar becomes compressed. The opposite side stretches far into space. Charged particles are guided toward the poles. The result could be auroras larger and brighter than anything in human history. At first, the lights might be beautiful. Then they would become a warning. Auroras might spread far beyond the Arctic and Antarctic regions. Skies over cities near the equator could glow red, green, and purple. People would walk outside and record the event. For a few minutes, it might become the most photographed night in history. But those colors would mean that high-energy particles were pouring into the upper atmosphere. Beauty would be the first visible symptom of a planetary emergency, because while everyone looks up, the chemistry above them begins to change. High-energy radiation can smash into molecules in the atmosphere. It can break nitrogen and oxygen apart. Those pieces can recombine into new chemicals. Some of those chemicals attack ozone, and ozone is extremely important. It forms a thin protective layer that absorbs much of the sun's harmful ultraviolet light. Without enough ozone, ordinary sunlight becomes more dangerous. The pulsar would not need to burn the surface directly. It could weaken the shield that makes sunlight safe. This is what makes the situation so deceptive. The first pulse would not necessarily make every person collapse. Houses would still stand, oceans would not instantly boil, trees might look completely normal. But above them, the atmosphere would be changing. The danger would grow quietly. Day after day, more ultraviolet radiation from the sun could reach the ground, and the smallest living things could be among the first to suffer. Near the ocean's surface live tiny organisms called phytoplankton. They are small, but they support enormous food webs. Small creatures eat them. Fish eat those creatures. Larger animals eat the fish. Phytoplankton also help move carbon through the planet's natural systems. If intense ultraviolet light damages them, the effect can climb through the entire food chain. A disaster in space could become a food crisis on Earth without touching a single farm directly. Plants need sunlight, but too much harmful ultraviolet radiation can damage living tissue. Some crops would handle the change better than others. Farmers might use protective covers. Greenhouses could filter dangerous wavelengths. Indoor farms would become much more valuable. But protecting entire forests, grasslands, and oceans would be impossible. Humanity could shelter some plants. We could not place a roof over the planet. And radiation would not be the only problem reaching the ground. Rapid changes in charged particles and magnetic fields can create currents inside long conductors. Power lines are long conductors. Pipelines are long conductors. Undersea cables are long conductors. Strong space weather events already create problems for electrical systems. A nearby energetic pulsar could produce a far more extreme environment. Grid operators might disconnect sections to protect equipment. The safest decision might be to turn parts of civilization off before the pulsar turns them off permanently. Cities would begin rationing power. Hospitals would switch to backup systems. Fuel deliveries would become critical. Internet connections would slow or disappear in affected areas. Governments would tell people to remain calm. People would immediately buy every battery, bottle of water, and roll of toilet paper they could find. The cosmic emergency would quickly become a very human emergency. The radiation is not one explosion. It is not a 10-second flash that ends. The pulsar continues spinning. 30 times every second, the beam sweeps across Earth. That is more than 2.5 million pulses every day. To the atmosphere, the pulses could blend into something closer to a continuous attack, and the pulsar is showing no sign of stopping. Then someone asks the question nobody wants to answer. Can we move out of the beam? Earth moves around the sun at roughly 30 kilometers per second. That sounds fast, but the beam is enormous by the time it reaches us. Moving the planet a few thousand kilometers would not solve the problem. We would need to change Earth's orbit by a massive amount. No rocket system has enough power to push an entire planet away quickly. Earth is not a spaceship. It has no emergency steering wheel. So perhaps we should block the beam instead. Imagine building a giant shield in space. It would need to protect Earth from radio energy, high-energy photons, and fast particles. A normal sheet of metal would not be enough. Gamma rays require thick shielding. And any shield large enough to cover Earth would need to be wider than the planet. Building it would require an unimaginable amount of material. Then we would have to keep it perfectly positioned. We cannot shield the whole Earth, but we might be able to shield small pieces of humanity. Rock is excellent protection against many forms of radiation. The deeper you go, the more material stands between you and the sky. Mines, tunnels, and underground facilities could become shelters. People might live beneath layers of soil and concrete. Water is also useful shielding. Deep underwater environments would be safer from some radiation than the exposed surface, but survival underground creates another problem. A bunker can protect people from radiation. It cannot produce endless food, air, and replacement parts by magic. Survival would depend on closed systems, underground farms, water recycling, artificial lighting, stored seeds, protected computers, medicine, machines capable of making replacement parts. Every community would become a small artificial world. A broken water pump would no longer be a minor inconvenience. It could threaten everyone inside, and only a fraction of humanity could enter such shelters in time. Who gets protected? Scientists, doctors, engineers, children, political leaders, farmers, people chosen by lottery? No answer would feel fair. Countries with more underground infrastructure would have an advantage. Wealthy people would build private shelters. Borders could close. Conflicts might begin before the radiation causes its greatest damage. The pulsar would test more than our technology. It would test our ability to cooperate. But our pulsar has another weapon, one that works much more slowly. The pulsar contains more mass than our sun. At 1,000 astronomical units, it would not rip Earth away immediately. The sun's gravity would still control the planets near it, but the solar system would no longer contain one dominant stellar mass. The sun and pulsar would begin responding to each other's gravity. Over thousands of years, their motion would form a strange new gravitational partnership. The planets might survive the first change. The objects farther away would not be so lucky. Far beyond the planets is a vast region containing frozen objects. This is the Oort cloud. These objects are weakly attached to the sun. A nearby stellar mass could disturb many of them. Some would be thrown away. Others could fall toward the inner solar system. Not tomorrow, not next month, but over thousands or millions of years, a wave of new comets could begin arriving. Even if humanity survived the radiation, the sky could remain dangerous long after the first crisis. Earth would not suddenly fly directly into the pulsar. The sun is extremely close to us compared with the pulsar. Its gravitational pull remains much stronger at Earth's location. Our planet would continue orbiting the sun. But over very long periods, the pulsar could alter the movement of distant objects and slightly reshape the solar system. The immediate killer is not gravity, it is energy. And that gives humanity one small advantage. We know what to fight first. During the first week, governments focus on immediate survival. Protect the electrical grid. Move satellites into safer modes if possible. Ground vulnerable flights. Distribute radiation detectors. Prepare underground spaces. Protect food supplies. Move seeds, medical equipment, and critical data beneath thick shielding. The world would begin transforming faster than during any previous crisis. The beam is not equally powerful everywhere. It has a center and an edge. Earth is not perfectly centered inside it. As our planet moves around the sun, the strength changes slightly. For part of the year, Earth moves closer to the beam's center. For another part, it moves toward the edge. This means the radiation will rise and fall in a predictable cycle. Humanity has not escaped. It has discovered the date of the worst pulse season. The strongest period will begin in 3 months. That creates a countdown. Underground spaces are expanded. Subways become shelters. Mines become towns. Libraries are copied onto protected computers. Seeds are gathered from around the world. Factories begin producing filters, lamps, batteries, and radiation-resistant electronics. The entire planet prepares to go below the surface. But 3 months is enough time to prepare only if civilization remains organized. Some people refuse to believe the warnings. Others spread false cures. Fake shelters are sold online. Groups claim the pulsar is a secret weapon. Supplies disappear from stores. Governments struggle to communicate clearly while communication systems continue failing. The scientific problem is difficult. The information problem may be worse. The pulsar attacks the atmosphere, but fear attacks society. As the peak approaches, people gather outside one final time. The sun sets. The sky glows with auroras across the entire planet. Children watch colors move overhead. Adults understand what those colors mean. For many people, this may be the last evening on the surface for months or years. Then, the shelter doors close. Above them, Earth enters the brightest part of the beam. Satellites on the exposed side begin failing in groups. Radio communication becomes extremely difficult. Power systems are divided into smaller networks to prevent massive cascading failures. The upper atmosphere glows. Chemical reactions accelerate. At the surface, ultraviolet levels climb. Unprotected exposure becomes increasingly dangerous. Humanity retreats beneath rock, concrete, and water. For the first time in history, almost every surviving human has the same ceiling: stone. Days underground become weeks. Weeks become months. There is no natural sunrise. Lights turn on in the morning and off at night. People exercise to protect their bodies. Children attend school beside water pipes and ventilation machines. Everyone learns the sound of every pump and fan. Silence becomes frightening, because silence may mean something has stopped working. Yet outside the shelters, life does not vanish completely. Deep-sea organisms remain protected beneath enormous amounts of water. Life inside rocks survives. Microbes hidden underground continue as if nothing has happened. Some plants in protected valleys or beneath artificial covers may survive. Earth has experienced disasters before. Life is flexible. It hides, it adapts, it waits. The surface biosphere would suffer terribly, but the planet would not become completely sterile overnight. The question is no longer whether life survives. The question is whether our civilization survives with it. Humanity begins adapting. Food production moves indoors. Robots perform short tasks on the surface. Vehicles use heavy shielding. Communities share energy through protected local networks. Old mines expand into permanent cities. The surface becomes a place people visit wearing protection, not a place where most people live. Our species becomes partly subterranean, but no bunker can solve the main problem forever. A pulsar's beams are powered by its rotation. As it releases energy, its rotation gradually slows. Eventually, pulsars become weaker. But eventually in astronomy can mean thousands, millions, or billions of years. Humanity cannot simply remain underground and wait for the pulsar to become tired. We need the beam to move, or the pulsar itself must leave. Then, astronomers detect a tiny change in the pulsar's position. The pulsar did not appear completely still. It is traveling through space. Neutron stars can move rapidly because the explosion that created them may kick them in one direction. Our pulsar is passing through the outer solar system. It will not remain 1,000 astronomical units away forever. But that does not automatically mean good news. Its path brings it closer before it moves away. The worst part of the encounter has not happened yet. In our scenario, the pulsar reaches its closest point several years later. The beam becomes stronger as the distance decreases. The particle wind intensifies. The outer solar system is disturbed more severely. Humanity faces a choice: remain divided in thousands of fragile shelters, or combine resources to build a smaller number of stronger, self-sufficient underground cities. The object that nearly destroys civilization may force civilization to work as one system. At closest approach, the night sky above the shelters is filled with radiation that human eyes cannot see. Instruments record the strongest pulses of the entire encounter, 30 times per second, again and again. Earth's magnetic field bends. The atmosphere absorbs energy. Protected systems shake under the pressure. Then, pulse by pulse, the readings stop increasing. They become stable, and finally, they begin to fall. The pulsar is moving away. As the pulsar continues along its path, Earth slides toward the edge of the beam. The pulses weaken. The particle wind becomes less intense. For the first time in years, ultraviolet levels begin moving in the right direction. The atmosphere will need time to recover. Ecosystems will need much longer. But the attack is ending. Opening the shelter doors, however, does not return the old world. The first teams emerge wearing protective equipment. They find damaged forests, abandoned cities, broken satellites burning through the atmosphere. Some ecosystems have collapsed, others have changed. The air is still breathable, the oceans remain. Life has survived in hidden places. Humanity now faces a task almost as difficult as surviving the pulsar: rebuilding a living surface. And above them, the pulsar leaves one final gift. The pulses are now weaker, but they remain detectable. Scientists use them to track the pulsar's movement with incredible precision. Future spacecraft could use pulsars like navigation beacons. The object that once acted like a cosmic weapon becomes a cosmic lighthouse again. It nearly ended our surface civilization. Now its pulse helps guide the civilization that survived it. But would a real pulsar encounter happen exactly this way? Not every pulsar is equally dangerous. Some are old and weak. Some produce powerful X-rays and gamma rays. Some beams would miss Earth completely. Distance matters. Age matters. Speed matters. And most importantly, direction matters. A pulsar could appear nearby without pointing its main beam toward us. In that case, the story would be very different. The pulsar itself is not the gun. Its alignment decides whether Earth stands in front of the barrel. Fortunately, no known pulsar is about to appear 1,000 astronomical units away. Stars cannot simply pop into existence beside us. This was a thought experiment, a way to understand how distance, radiation, gravity, and Earth's atmosphere interact. The real pulsars we study are extremely far away. Their pulses reach our telescopes as faint signals, not planet-ending attacks. And perhaps that is the most amazing part. Something only 20 kilometers wide can contain more mass than the sun. It can spin faster than a kitchen blender. It can send perfectly timed pulses across thousands of light years. And from a safe distance, those pulses help us study space, test physics, and imagine navigation between the stars. A pulsar near Earth would be a nightmare. A pulsar far away is one of nature's most extraordinary clocks. So here is the next question. What would be worse, a pulsar appearing near Earth or Earth suddenly orbiting one? Well, at least for now, we don't need to worry about the answer yet.